Welcome to the class. Today's class is about spectral analysis of alkanes and cycloalkanes. In the previous class, we discussed about the analysis of spectrum. From today onwards, I would like to give a detailed picture of all the functional groups that are present. Okay, so one by one I will take. So today I am starting from hydrocarbon. Hydrocarbons are saturated hydrocarbons and unsaturated hydrocarbons. So today's class is about saturated hydrocarbons. In the saturated category, here I am choosing acyclic compound and also cyclic compound. So acyclic saturated compound, that is acyclic saturated hydrocarbon, and cyclic saturated hydrocarbon. So today's discussion is about alkanes and cycloalkanes only, right? Before going into the detailed study of the spectrum of alkanes, first of all let me introduce the two main concepts. Those are intensity and shape of an absorption band. How does the intensity of an absorption band changes? What property is applicable or influencing the property, that is intensity? So here the intensity of an absorption band depends on the change in the dipole moment of the bond. Okay, so when you feel the dipole moment for a particular bond, whenever the difference between the two atoms is large, that is electronegativity difference between the two atoms must be very large, then there must be creation of dipoles on the two atoms, so that you will find particular dipole moment for that bond, right? So see here, the intensity of an absorption band depends on the change in the dipole moment of the bond. If greater is the change in the dipole moment, more intense is the absorption band. So that is the first point. Okay, so the intensity is depend on the change in the dipole moment. So here I am taking an example OH, NH and CH. So NH and also CH. So here hydrogen is constant, one of the atom is constant and you are changing another atom. So here it is oxygen, here nitrogen, here carbon. From oxygen to carbon, what happens? The electronegativity decreases. So which one is having more electronegativity? Oxygen. So the electronegativity difference between the two atoms will be more for the case of OH bond. So as the electronegativity difference will be more, then the dipole moment experiencing is also more for the case of OH bond. Whenever you apply a particular IR radiation onto the bond, the change in the dipole moment will also more for the compound OH, because the polarizability is more here. It is dependent on the factor, that is polarizability. Okay, so more the polarization, more the, of course not polarizability, it is polarity. So more the polarity, more will be the change in the dipole moment. So see here, OH will experience more polarity than compared to NH. NH will experience more polarity than compared to CH. So out of these three bonds, which one will give the more intense bond? Due to the more polarity, OH will give more intense band. Okay, so this must be the more intense band. Which one? OH band. So it is depending on the factor that is polarity. Okay, right. And if you want to compare the values also, OH will give the vibrational frequency or absorption band at about 3600 centimeter inverse. This is the rough idea. And NH will give the absorption band at 3500, almost 3500 centimeter inverse, and CH will give the absorption band at around 3000 centimeter inverse, 3000 to 3100 depending upon the conditions. So see here, it is more intense peak. So this is just absorption at different values. The band which is having OH will be more intense band than compared to NH, and it is more intense than CH. Right. Now let us focus on the other point also. The intensity of an absorption band may also depend on the number of bonds responsible for the absorption. If suppose the number of bonds responsible for the absorption increases, then the intensity will also increases. That means number of bonds increases, intensity of absorption will also increases. Suppose here I am taking the example methane and octane. So both the two compounds, if I want to investigate, here I gave the answer also. Octane will have a much more intense CH peak than methane. How? Because methane, it is having CH4. This is the molecular formula for methane. If you want to write the molecular formula for octane, it would be CH3 CH2 taken 6 times CH3. Right. So if you count the number of bonds, here the number of bonds present in methane would be 4, because the carbon atom which is attached to 4 hydrogens. So total number of bonds present in methane would be just 4 only. But if you see here in the structure of octane, you find more number of bonds. If the number of bonds are more, then what about the absorption? Yes, the absorption must be more. That means octane will give more intense peak than compared to methane, even though the two compounds are coming under the same category, that is alkane. One of the alkane is giving more intense peak than compared to another one due to the presence of more number of bonds present in it. Right. If you want to compare other compounds also, you can take. You can compare the compounds like hexane. Hexane compare with propane. Which one will give the more intense peak? Absolutely, hexane will give the more intense peak. Like that, you can find any of the example. Right. And one more point that gives the intensity of an absorption band, that is concentration. If the concentration of the sample increases, then it will give more intense peak, because more concentrated sample will have more number of absorbing molecules. Therefore, more the absorbing molecules, more the intensity also. That means if you suppose to compare concentrated solution and dilute solution. So concentrated means number of molecules present. Concentrated is nothing but the major number of molecules present in the solution. So generally it will be solute plus solvent. If the solute concentration is solute amount is more, then we call the solution as concentrated solution. If the solute amount is less than compared to solvent, then we call the solution as dilute solution. So here solute is nothing but our compound. Our compound is used for the investigation. So if at all the compound that is used for the investigation is more quantity, that means more molecules are present in the solution. More molecules, absolutely they will absorb more IR radiation, and it will give more intense peak. If suppose for dilute solutions less number of molecules are present, so that's why least absorption will happen, and vice versa it will give least intense peaks. So concentrated solutions will give most intense peaks. So that is the technique to separate concentrated solution from the dilute solution. It is also one of the application actually. If suppose they are giving ethyl alcohol for you, ethyl alcohol, if you want to investigate through IR spectroscopy, they are giving in two different proportions. One is concentrated and the another one is diluted. Both the two compounds will give the same type of spectra only, but depending upon the intensity of the peak only, we can differentiate the two compounds. One is the concentrated solution and the another one is the diluted solution, right? So it is depending upon the intensity, right? Next factor is shape of an absorption band. A shape of absorption band can be helpful in identifying the compound which is responsible for an IR spectrum. Shape means some peaks will give sharp peaks, and some bonds will give broad peaks. How can we identify? So here I am taking the example OH and NH. So OH means alcohols, NH means amines. If you take the compounds alcohols and amines, OH stretching or OH stretching frequency or OH vibrational frequency and NH vibrational frequency will show at somewhat similar wave number, which is at about 3100 centimeter inverse. Then how could we separate which one is OH and which one is NH? It is depending upon the shape of the band, right? So how does the shape of band is different for OH and NH? Now let us see here. An NH absorption band which is at 3300 centimeter inverse is comparatively narrower and it is less intense than OH absorption band, right? So alcohol and amine are taken for investigation. Both the compounds are giving at the same range of IR wave number, but how can we identify? Depending upon the shape of the band. So OH band will be a broad band. That means a band can be look like this, broad band. But the band which is for NH band, it is a narrow band. Narrow means it will look like a sharp band. So see here, the shape is different, right? It will look in a narrow manner and it is look like a broader manner. So by seeing the two bands at the same value, we can differentiate that it is for NH and this is for OH. Like that we can differentiate the peaks. Now let us come to OH category only. So OH is present in the case of alcohols, and it is present in the case of carboxylic acids also. That means ROH, it is having OH bond, and for the case of carboxylic acid also you are having OH, right? So how can we differentiate these two OH? Here in the carboxylic acid, the OH absorption band will be observed at the range of 3300 to 2500 centimeter inverse. That means it is a broader peak. So it will look like this, a broader peak than compared to OH. Generally we already given the statement that is OH is a broad peak. So maybe OH will be like this, a broad peak. But here for the case of carboxylic acids, due to the presence of hydrogen bonding, a OH will give a broader peak. So here you are having narrow peak, broad peak, broader peak. So narrow peak is responsible for NH, broad peak is responsible for OH, and broader peak is responsible for OH only, but the compound is different, that is carboxylic acid. So this is the way of identifying the bands that is present in the spectrum. If nearer values are coinciding, we can find depending upon the shapes, right? Yes. Now let us discuss about the main concept, that is spectral analysis of saturated hydrocarbons, that is saturated acyclic hydrocarbon. So in this category I am taking alkanes. So what is the formula for alkanes? CnH2n plus 2. Simple example, C2H6. Okay, so this is nothing but ethane molecule. If you want to write the structure of ethane molecule, 2 carbon atoms are found. 2 carbon atoms are connected by a single bond, and remaining sigma bonds are with hydrogens. So totally 6 hydrogen atoms are present. One carbon atom is attached to 3 hydrogens, and another carbon atom is attached to 3 hydrogen atoms. Now if suppose you want to give the analysis of a particular compound, any alkane, here you can find which type of connections. Here you are having only single bond connections between the atoms, because we are studying about saturated hydrocarbons. So the saturated hydrocarbons will have a single bonds only, and the type of atoms that are involved in the single bond must be also find out. So here the type of atoms must be, here carbon and hydrogen are participated in the bond formation. So CH bonding is present here. Here you are finding carbon-carbon bond formation, right? So if suppose you want to find the arrangement of this category, that is here also CH, here also CH, and here CH, all the connections are CH only. That means entire molecule will give only 2 types of connections, that is CH connection and CC connection, right? So how many absorption bands are supposed to find here? Yes, for CH 1 absorption band, for CC 1 absorption band generally. But CH 1 absorption band means absorption due to stretching as well as bending. So there is again differentiation. Okay, right. So in the IR spectroscopy, CH will be present in which region? It is found in functional group region. Is it right? So in the functional group region you will find the CH absorption band, and CC absorption band will be found where? Yes, it is found in fingerprint region. Right? So functional group region is present 4000 to 1500 centimeter inverse. In between this range we have functional group region, and where the fingerprint region is present, it is present from 1500 to 667 centimeter inverse. So this region is for fingerprint region, or it may be sometimes 400 also. Okay, right. Now what are the bands and what is the spectrum of alkanes? Now let us see. So in the case of ethane molecule, here you are having the arrangement of carbon atoms. 2 carbon atoms are present, 2 methyl groups are connected. If suppose you are taken a propane molecule, so propane molecule means a methyl group which is connected by a methylene group with another methyl group. So here 2 methyl groups are connected by 1 methylene group. If suppose you want to write the formula for butane, so butane will be like this: a methyl group which is attached by another methyl group through 2 methylene units. Right? So whatever the compound you take, there you can find CH and CC absorption only finally, right? But a variation is groups. So here only methyl groups are present. Here in addition to methyl groups we are having methylene group also. By increasing the number of carbon atoms, you can find the increase in the methylene units. Methyl units must be 2 only. So the number of methyl units present in the compound must be 2 only for the higher alkanes, but the count will be vary for methylene units. Methylene units can be increased one by one, right? Now we have to give the clarity for methyl groups and methylene groups. Generally, CH absorption band for alkanes we will found 2 types of absorption bands: CH absorption band and CC absorption band. So CH absorption band will be present in the range of 2970 to 2860 centimeter inverse. So this is the range of absorption band for the case of alkanes, right? So here I am giving the detail for methyl group and methylene group also. Methyl group is usually show 2 strong and distinct bands. One band is at 2970 centimeter inverse. So this is the first band. It is due to asymmetrical stretching, and the another one is at 2860 centimeter inverse. This is due to symmetrical stretching. So see here the variation in the number. Asymmetrical stretching is more and symmetrical stretching is less. Why? Because a stretching is due to the same type of force for the case of symmetrical stretching. That means if it is the bond between the 2 atoms, symmetrical stretching means two atoms will be stretched the two atoms will be stretched in a equal force. Okay, what about asymmetrical stretching? One mode will be, suppose I am taking this example. If the two bands or two bonds are elongation or participating in elongation, or two bonds are participating in contraction, then we call this type of stretching, or we call this type of movement as symmetrical stretching. Both the connectivities will follow the same type of movement. If suppose one of the atom is compressed, another atom is moving elongated, then the movement of the two atoms is asymmetrical in nature. So one is compressed, another one is elongated. If this one is compressed, it must be elongated. So the pattern of movement is not a symmetrical, that means it is a asymmetrical stretching. Generally asymmetrical stretching will experience more strength. Okay, so more energy is required for asymmetrical stretching. So the wave number is also more for asymmetrical stretching. So that's why here we are experiencing more value for the case of asymmetrical stretching for methyl group, right? If suppose methylene group is present, methylene group can show asymmetrical stretching at 2930 and symmetrical stretching is at 2850 centimeter inverse. So this is for methyl group and this is for methylene group. So depending upon the group present, we can find a particular value, right? So this is for stretching. What about bending? Bending is also possible, right? Generally CH will give stretching vibrations and also bending vibrations. Stretching will be observed at the range of 2970 to 2860 centimeter inverse. So this is the range of CH stretching vibrations. Now what about the CH bending vibrations? Yes, CH bending vibrations also given for the clarity, that is methylene and also methyl group. If suppose methylene group is present, methylene group will have two bands. Okay, so this is for methyl group. So this is for methyl group. Methyl group will exhibit two bands at 1380 centimeter inverse and 1460 centimeter inverse. So these two are the possible bands for the case of methyl group. So these two are bending vibrations. Okay, so stretching vibrations just I have given in the previous slide for methyl group and methylene group. And here for methyl group there is a possibility of 1380 centimeter inverse and 1460 centimeter inverse, two possible bands for methyl group. If suppose methylene group is present, so due to the presence of methylene group, you will have totally 4 types of bending vibrations. That means 4 bands are appeared. Of course, 4 bands means not exactly 4 bands are appeared in the spectrum. Any one of the band can majorly find. Okay, the first one is 1465. So the band at 1465 and one more band is present which is at 720 centimeter inverse. This is due to rocking. So this is very important. 720 centimeter inverse for methylene unit is a characteristic bond. So it is the characteristic absorption band for methylene group. And also 1305 and 1300. So these two bands are also appeared in the spectrum. Of course these two are rare. The possibility of visibility of the two absorption bands are more common, these two absorption bands. Okay, right. So here you are having 1460 band for methyl group. Here also you are having 1460 band for methylene unit. Then how can you distinguish a methylene group from methyl group? Yes, that is due to the presence of the band at 1380. Okay, so see here you are having the two bands at 1380 and 1460 for methyl group, but for methylene group you are having 1465 band only. At 1380 there is no band here. So this is the identification for detecting the methyl group. So 1460 band is appeared for methyl group as well as methylene group, but 1380 band is observed for the case of methyl group only. It will not found for the case of methylene unit. So this is one way of finding a methyl group and methylene units, right? Okay, now I would like to give some more detail about alkane category. So this 720 centimeter inverse is responsible for straight chain higher alkanes. So wherever you find 720 centimeter inverse absorption band, it is for straight chain higher alkanes. Higher alkanes means there is a number of like the case of octane. So in the earlier case I take the example octane, right? CH3 CH2 taken 6 times CH3. So it is coming under the higher alkane because the number of CH2 units connected by two methyl units must be high here. So if the number of methylene units present in the system is greater than 4, then we call the system as higher alkane. Okay, so this is very important. When we call the alkanes as higher alkanes, whenever the methylene units present in between the two methyl units is greater than 4, then the type of alkanes we call as higher alkanes. So this is the first higher alkane because the number of methylene units are greater than 4. So if suppose the number of methylene groups are greater than 4, then definitely you will find the peak, absorption peak at 720 centimeter inverse. So this is the identification for higher alkanes. So by seeing the picture, by seeing the absorption peak at 720 centimeter inverse, you can find or you can give the information that yes, the alkane is a higher alkane. Okay, because the number of methylene units are more than 4, then only you can get the absorption peak at 720 centimeter inverse. So this is for straight chain alkanes. So this is the identification for straight chain alkanes. If suppose the alkane is branched one, so branched alkane, how can we differentiate branched alkane from straight chain alkane? If suppose there is no presence of there is absence of 720 centimeter inverse peak, then it will give the clearance that the alkane is not a higher alkane, it may be lower alkane, or it may be a branched alkane. That is the identification, right? So if suppose the compound is branched alkane, for the case of carbon which is attached to two methyl units, then we call this arrangement as isopropyl group. Is it right? So whenever you are having the arrangement or structural information like isopropyl group will be given two absorption bands. So if suppose the two absorption bands are found in the range of 1397 centimeter inverse and 1370 centimeter inverse, then you can give the clarity that yes, your compound is containing isopropyl unit. Okay. So this is the key idea in the identification of isopropyl group in your compound, right? Suppose the carbon atom is attached to 3 methyl groups, then this structural information we call as tertiary butyl group. So the presence of tertiary butyl group in your compound will also particularly give two absorption bands near at 1385 centimeter inverse, and this one is constant 1370 centimeter inverse. So depending upon the two bands at the near values, so here it is 1397 and 1370. So in the spectrum, wherever you find the absorption peaks, then it will give us the clarity that your compound is having isopropyl unit. If suppose you are having 1385 and 1370 peaks, two absorption peaks, then it will give us the information that your compound is having tertiary butyl group. So these are the major ideas for detecting the groups that are present in alkanes, whether methyl groups are present, methylene groups are present. If suppose methylene units are present, is it coming under higher alkane or lower alkane? If suppose it is not higher alkane, then it must be lower alkane, right? So that is about straight chain alkanes. If that can be found out by this 720 peak. Okay, 720 peak will give us the information that the compound must be a higher alkane. If at all 720 peak is not found in your spectrum, then it may be a lower alkane or a branched alkane. If suppose the alkane is branched one, these two are the identifications. Is it isopropyl unit or is it having tertiary butyl group? So depending upon these two peaks, 1397 and 1370, it will give us the information that isopropyl unit is present. But presence of these two peaks will give us the clarity that tertiary butyl group is present in our compound. Okay, so this is the detailed information about the analysis of alkanes. So I think it is a mistake that it is not cycloalkane, it is just alkane. Okay, so now I would like to show the spectrum of any alkane. See here, this is the spectrum of octane. See, on y direction or y axis you are taken percentage transmittance, and on x direction we are taking wave number. So with respect to percentage transmittance and wave number, we are having this graph, and this graph we called as spectrum. In IR spectroscopy we are studying this entire phenomenon, and if you see here the small clumsy peaks you are finding here, right? So there is no much absorption. Okay, there is no much transmittance. Of course, there is no much absorption because the percentage transmittance is observed above 90. So above 90% means there is not much absorption. If at all there is no absorption by the compound, then the incident radiation will directly reach us to detector with high intensity. So that's why that transmitted light will have high intensity. That means there is no absorption. Detector will find the information and it is giving to the analyzer. So that's why there is no information about the absorption at the value of this. Whenever you reach here suddenly the peak is present and this is having low transmittance. Low transmittance means here you see the transmittance is less than 10. The percentage of transmittance is less than 10 means almost maximum amount of radiation is absorbed here, and this region is responsible for CH stretching. Okay, so see here you are having a peaks which is at about 2971, and here you are having 2863. So these peaks will give us the information that CH stretching vibrations for an alkane, right? So see here a structure of alkane is given. In the structure of alkane we are having CH and CC absorptions only. So here I gave the information about CH stretching vibrations. So CH stretching vibrations will occur at this range. Now come to here you are having 1470 and 1383. So those two peaks are observed here. So 1380 is responsible for, yes, it is responsible for methyl group bending. So CH bending for methyl group, and this is responsible for CH bending for methyl group as well as methylene group. So this is the characteristic nature of your compound. By seeing this two absorption bands, we are confirming that yes, our compound is alkane because we are in the functional group region. Whenever we are coming into fingerprint region, this fingerprint region having the absorption bands will give us the information that the characteristic nature of your compound. So in your compound methyl units are present, methylene units are also present. That is the characteristic idea by seeing these two peaks. Now come to the another peak. At 728 you are having one peak. If at all you are finding the 728 peak, it is because of a long chain alkane. Okay, long chain alkane means the number of methyl units must be more than 4. So more than 4, then you will have this peak, that is 728 peak. So count the number of methyl units here: 1, 2, 3, 4, 5 and 6. So more than 4 is present, right? So that's why octane is supposed to give 726 peak. So by observing these peaks, that is absorption bands, we can give the structure of the compounds also. If at all we may not know the structure of the organic compound, by visualizing the absorption bands in the spectrum, we have to find out the structure of an organic compound by the detailed study. Okay, so this is the information about interpretation of IR spectrum of an alkane. Now let us come to cycloalkanes. So how can we analyze cycloalkanes? Right. So cycloalkanes means this is a cycloalkane, right? And this is also a cycloalkane. This is also a cycloalkane. So saturated hydrocarbon in cyclic manner. So this is cyclopropane and this is cyclobutane and this is cyclohexane. So if you compare all the compounds, for cyclopropane the structural arrangement would be like this. All the carbon atoms are connected by single bonds and you are finding only CH2 units. There is no methyl groups. Only methylene units are present for the case of cycloalkanes. If you consider cyclohexane also, so cyclohexane, this is the structural requirement for cyclohexane. Is it right? So for the case of cyclohexane, you are finding only CH2 units. There is no CH3 units. That means CH3 unit is not present for the case of cycloalkanes. For the identification of CH3 unit in the spectrum, which one is the characteristic peak? 1370 peak. So if at all 1370 peak is absent, then it may be a cycloalkane. Generally alkanes will supposed to give methyl peak, the peak which is responsible for methyl group. If it is not present, then it must be a cycloalkane. Okay, so cycloalkane 1370 centimeter inverse peak will be absent and it will give only 1460 centimeter inverse peak, which is for methylene unit. And what about carbon and carbon? So there is a linkage between carbon and carbon also, right? So CH, CC, here also you will find these two types of stretchings. So CH will have stretching and also bending vibration. Even CC also will give two types of vibrations. One is stretching and the another one is bending. CC stretching vibration for cycloalkanes will be found at the range of 1200 to 800 centimeter inverse. So this is the stretching vibrational frequency for C single bond C. But for the case of bending, if you want to find the bending vibration for C single bond C, it will not find in the IR region because CC bending vibrations are less than 500 centimeter inverse. Our IR region ends by 667 centimeter inverse only. So that means we cannot able to find the CC bending vibrations in IR spectra. So that's why we can found only CC stretching vibrations in our IR spectra. Particularly they are found in the fingerprint region. Okay, right. As in the case of acyclic saturated hydrocarbon, that is alkane, CH stretching vibration will be same for cycloalkanes also, because for CH, that is CH stretching vibration, for the case of alkanes we are having 2960 to 2850. At this range we found CH stretching vibration. Like that you will have for cycloalkanes also, you will have the vibrational peak or absorption peak at the range of 2960 to 2850. Now let me show you the analysis. In case of unstrained cycloalkanes, the CH stretching frequencies are same. Unstrained means there is no strain. So unstrained cycloalkanes will have the stretching frequency same as in the case of cyclic, that is acyclic compounds. If suppose sterically strained cyclic compounds are present, the CH stretching frequency will be normally occur at slightly higher frequencies. Slightly higher means if suppose cyclohexane I am taking, cyclohexane, it is an unstrained cyclohexane, so it will have the CH stretching frequency at 2950 to 2860 centimeter inverse. If I want to show the strained cyclic compound, I am taking example cyclic propane. So cyclopropane, which is having sterically strained means I am introducing the one group also. So methyl group I am introducing. So in sterically strained cyclic compounds, the CH stretching frequency normally occurs at slightly higher frequencies. Slightly higher means it may be at around 3100 to 2990. So this is the range of absorption frequency for CH in the case of sterically strained cyclic compounds. So see the variation. It is unstrained cyclic compound and this is sterically strained cyclic compound. So due to that we can differentiate the cyclic compound which is strained one or unstrained one depending upon the values present in the spectrum, right? And methylene units, come to methylene units. Methylene CH bending vibrations in cyclic alkanes. Cyclic alkanes means just cycloalkanes shift slightly to smaller frequency as compared to their acyclic counterparts. So in the case of acyclic counterparts, we have CH2 bending vibrations at 1370 and 1465 centimeter inverse. Is it right? Of course 1370 is not found for methylene unit. It is just 1305 centimeter inverse or 1310 centimeter inverse. So at the range of 1305 and 1310 and also 1465 centimeter inverse is for methylene CH bending. So for cycloalkanes, you are experiencing slightly smaller frequency as compared to acyclic counterparts, means so slightly decrease in a frequency, means it may give at around 1440 centimeter inverse. So the absorption peak is found a slightly decreased frequency than compared to acyclic counterparts. So that's why it will be at around 1440. So this is the major idea in the identification of cycloalkanes. So depending upon the strained one or unstrained one, or again you have to find out the CH bending vibration. Okay, now I will show you the spectrum of one of the cycloalkane. So this is the spectrum of cyclohexane. So cyclohexane, this is the molecule of cyclohexane. For the cyclohexane molecule, here you are having the bands. So one absorption band is found here. So this is at about 2920. See here, this line indicates 2900, a slight excess. So that's why I am taking 2920. Now you extrapolate this point also, it will be at around 2850 centimeter inverse. So the two bands that are appearing at 2920 and 2850 is due to CH stretching. So one band which is having higher value, this is due to asymmetrical stretching. One band due to lower value, it is due to symmetrical stretching. Okay, so asymmetrical stretching and symmetrical stretching of CH bond. Right, now here also you are finding one absorption band. Now you want to extrapolate this line towards the peak, at which point the value coincides, you just want to identify here. So it is 11, 12, 13, 14. So it is at about 1440. Okay, almost 1440, right? So slight decrease in the acyclic counterpart. So at 1440 centimeter inverse, you are finding the absorption peak. This absorption peak is due to methylene group. So it is the CH bending of methylene group at 1440 centimeter inverse. Okay, right. So CH stretching is present, CH bending is also present. Now we have to find out CC stretching, because for the case of cycloalkane as well as alkane case, we are having only CH and CC type of absorption bands. CH is for stretching and bending and CC is for only stretching, right? So this, we are not having a particular idea here. Yes, so the peak which is at around 1200, and here also you are having peaks, whether it is or this may be. the intensity of the peak. You have to find out the intensity of the peak. This is in low intensity, right? Now if you see these two peaks are high intense peak than compared to this. So if you want to consider this peak, you can, so if you want to extrapolate this one, it will match at 900. So 900 centimeter inverse, you are having one peak, that is nothing but CC, stretching vibration. Okay, so totally you are finding CH stretching, CH bending and CC stretching in the case of IR spectrum of a cycloalkane. Okay, fine, right. So I think it is already explained. So this is the overall view of spectrum identification and spectral analysis of saturated hydrocarbons, that is acyclic saturated hydrocarbons and cyclic saturated hydrocarbons. Okay, right. So by seeing the values, you can find the compounds, you can find the nature of the compounds also, if it is straight chain alkane or branched alkane. If it is branched, is it having tertiary butyl group or isopropyl group? Depending upon the absorption peaks, you can find out the nature of the alkane also. Okay, so this is about today's class. Thank you. Thank you.